Okay, in this video we're introducing free body diagrams briefly. Free body diagrams, or FBDs, are used to diagram forces acting on an object or a collection of objects, which we call a system. So we're looking at force acting on an object or a collection of objects, which we call the system. The object or system is represented by a dot at the center of mass. So it's a free body diagram because you free up the object or the system from the rest of the complicated environment that's around it, and you just focus on one object or one system, and you represent it with a dot. And that dot should go at the center of mass of that object. Forces acting on the object or system are represented by vector arrows. So forces are vectors, so they have magnitude and direction, so we use vector arrows to represent them. The arrows must point in the direction of the force. Because forces are vectors, they have a direction, and the length of the arrows must be proportional to the magnitude of the force. So the magnitude is how much? Like, how strong of a force is it? Is it 10 newtons or 100 newtons? A 100 newton force is going to have a longer vector arrow than a 10 newton force. Only forces are represented by vector arrows. We're not diagramming anything else. Velocity, acceleration, nothing else goes on the free body diagram. It's just forces acting on that object or that system. And we have to have the free body diagrams done properly before you do anything else. Usually you do your free body diagram and then you look at your second law. Sigma F equals ma. Mass of force equals mass times acceleration. And so if you don't have the forces diagrammed properly, you don't know which forces are pointing in what directions or how many they are or what types of forces they are, then you're not going to be able to solve anything. So the free body diagram is a really good visual to set up a problem or a scenario that you need to solve. So we're going to do an example. I have a coffee mug sitting here on a table, and I wrote out a few steps that are appropriate to follow for drawing free body diagrams. 1, choose a coordinate system. That means pick your axes, how your axis is going to be laid out, and decide which directions are positive and negative. So you just have to deal with x and y axes, just 2 dimensions there. And you need to say which direction on each axis is going to be your positive or negative direction. You can pick whatever you want, you just have to be consistent with it. Like, once you pick the right is the positive direction on the x-axis, make sure you keep the right, the positive direction, the whole time you're working the problem. Represent the object or system you're analyzing with the dot on its center of mass. Okay? Draw all forces acting on the object or system using vector arrows. The tail of the vector should always start on the dot. The arrow of the vector should always point in the direction of the force. And the length of vectors should be proportional to their magnitude. That is, larger magnitude force should be a longer arrow. If forces are at an angle, you must resolve them into their x and y component parts. We won't start with that, but we'll get to that where we'll have forces that are in at an angle in a slightly different direction. They don't directly point along the x or y axes. They're not necessarily parallel to either axis. So we got to break them up into our parts, just like when we had some launch velocity, say for a projectile that was at an angle, we needed to find the velocity in the x direction and the velocity in the y direction. Got to break it up into its x and y, or horizontal and vertical component parts. Always consider the acceleration of the object. If it's accelerating, its state of motion is changing. It has a change undergoing for its own momentum. If it's accelerating, then there must be some unbalanced net force acting on it. There must be some unbalanced net force that's causing this change in state of motion. That's if it's accelerating. If it's not accelerating, then there must be no forces acting on it, which we're probably never going to see, because usually we always have something acting on an object. So if it's not accelerating, either no forces acting on it, or, much more likely, all the forces acting on it must balance out, and the net force must be 0. As a reminder, we care about net or total force, F sub net if you like, and that means we have to consider all the forces acting on the object, and we figure out, basically add all those forces together and see what the total force is. So you can write F net, or you can write what I write, which is sigma F, and that means total force. Total force acting on the object. So that takes into account the magnitude of all the forces and their directions. So let's take our coffee cup, for example. I'll draw my dot at the center of mass. I don't know where the exact center of mass of this coffee cup is. We know it's made up of tons of atoms. but we don't need to draw a free-body diagram for each individual atom. We just say, look, the coffee cup is the object, or it's a system of atoms, but it's one object. We represent it with a dot at the center of mass. That's where I think the center of mass might be, so I'm putting the dot there. I need my axes. I need to decide what's going to be the x and y axes. Now, this is just some normal coffee cup sitting on a table on the surface of the Earth. And you already probably know what forces I'm going to end up drawing on the thing. It's sitting at rest relative to the Earth, so it's not accelerating. It's not speeding up, slowing down, or changing direction. So here are going to be my axes. It's kind of like the normal way you would draw x and y axes. And I need to give what directions are going to be positive and negative. You could do something like this, say that's positive y and that's positive x, or a lot of times you'll see this indicating the positive directions. Something needs to be there to indicate which directions are positive and negative. All right, so I got my dot. I have my axes. I've defined which directions are positive and negative. So now I'm going to go and draw my forces. I'm going to use purple again. So I think what forces are acting on this cup? Well, I have gravity for sure. That's what's pulling the cup in the downward or negative y direction. So I have the tail. You see the tail is going to be on the dot, and so my arrow is down there. I don't like that arrow. Let's try again. All right, that works. So the tail is always on the dot, representing the object or system, and the arrow is pointing in the direction of the force. Then I need to label every force that I draw, so I don't lose track of which force is which. So for the gravitational force, we use the symbol F sub g, which equals mg. So you can label it as Fg, or you can label it as mg. And I'm going to write Fg equals mg to remind you that that's what Fg is, gravitational force. Remember, that's also the weight of this coffee mug. Now, I know there's another force acting on it because the coffee mug is not accelerating, and right now I have an unbalanced force if I leave my diagram like this. But it's not accelerating, so that gravitational force must be balanced out. By what? Well, the force of the table pushing up on the coffee mug. And I need to draw that in the upwards direction. I'm trying to draw equal length as Fg, because if they balance out, then the vector arrows should be the same length. So I'm looking at my ruler here. I got one long line, 2, 3 it looks like. That'd be 1, 2, 3. It looks longer on the top. We'll see it in a second. But that's going to be my normal force, F sub n, because we said the normal force is a contact force that's perpendicular to the surface of contact. Now, in this case, since it's just at rest, there's no acceleration, the normal force should balance out and be exactly equal in magnitude, or the amount of Fg. I have my dot, my axes, my directions, my forces drawn as vector arrows with the tails on the dot and the arrows in their directions, and I have all those forces labeled. Now, what the free body part of the free body diagram description is that we want to free up the object from its actual environment. So what the free body diagram actually is just this part. All right, this is what we want to draw. We want to be able to look at a picture or imagine a scenario, like over here with the coffee mug. We want to free up the object or system from its environment and represent it just with this. This is the free body diagram, just this stuff. Okay, so I have just the dot and the arrows, my axes, my directions, and then I can start to analyze stuff. Now, one thing real quick about, I have grid paper here, so like if you used a ruler or you had grid paper, you could ensure that the lengths of your arrows are going to be the same or proportional, depending on if there's one that's larger than the other. But if you're not, and usually you're not probably going to be using a ruler or grid paper, if you just have a blank sheet, then you can indicate that these forces are equal or balanced by just drawing a couple congruency lines there, and then that lets everybody know that you're trying to indicate that the vector arrow for normal force is equal in length or equal in magnitude to the vector arrow for Fg. After we get this stuff done, our free body diagram is now done for our coffee mug, but where we take this is we're going to be able to say, okay, wait, the thing's at rest, it's not accelerating, so that means acceleration is 0. If the acceleration is 0, Newton's second law, F equals ma, or sigma F equals ma, tells us that the net force, or the sum of all the forces, must also be 0. A is 0, sum of forces must be 0. If that's the case, then therefore, the sum of the forces is 0, then the only two forces I have are normal force and gravitational force. That means normal force must be equal to gravitational force. It won't always be equal to gravitational force, but in this scenario, it definitely is. So Fn equals Fg. Fg equals mg, mass times gravitational acceleration. Therefore, normal force is equal to mg. So that's something that I could then add to the diagram. I could say now I know normal force is equal to mg. Those are the basics of our free body diagramming. We always want to make sure that we follow these steps. You always need to choose a coordinate system, pick where your axes are going to be, indicate the positive and negative direction, represent your object or system with the dot, draw your forces proportionately with vector arrows with the tail starting on the dot and the arrow pointing in the direction of the force. If forces are at an angle, like if we had a force like this coming off to the side, and we've got some angle here, we would have to break it up into its x and its y component parts. So if this blue line I drew was F, then I would have F in the X direction, and I would also have F in the Y direction. And if you have an angle, you guys know where I'm going with this, just like we did with projectiles, then F in the X direction is going to be F cosine theta, my hypotenuse in blue times cosine theta, and in the Y direction, Fy is going to be F, the hypotenuse, times sine theta. So that's all we mean by breaking up or resolving the force vector into its component parts. Consider the acceleration of the object. In the case of the coffee mug, I considered that, and I said acceleration is 0, and I can draw conclusions from that, namely that the normal force must be equal to mg. All right, that's all for free body diagrams for now.